Swayam Prabha. Digital India. Educated India.
In the previous lecture, we were discussing about the lubrication theory, and we eventually derived the governing equations for the leading order velocity component along x along with the boundary conditions. So, before proceeding further, I will try to summarize what we have discussed so far, so that you can recapitulate and then we will move forward. So, if you look into the view graph which is there, then basically you have a narrow passage where the length scale along y is much smaller than the length scale along x. So, the epsilon, which is the length scale along y by the length scale along x, is considered to be much less than 1. So, we have used various non-dimensional parameters. I will go through these slides pretty quickly because this is just to sum up, not to give you any new concept. And we have obtained the velocity scale along y in terms of the velocity scale along x using the continuity equation. Certain important notes for non-dimensionalization: we have used the characteristic values of the variables to non-dimensionalize the pertinent variables. This is a very important step. This ensures that all non-dimensional variables and their derivatives have order of magnitude of 1, that is, variables are of the order of 1. This means that the contribution of a variable or its derivative in a given equation solely depends on its coefficients, because the derivative is of the order of 1. This process thus enables us to neglect certain terms in the corresponding equations based on only the coefficients. The concept is of utmost importance in fluid mechanics, as a number of methods employed in this subject come straight from this concept. For the sake of completeness, we will assume that the body forces Fx and Fy act along x and y directions. These forces might be gravity, magnetic field, electromagnetic effect, whatever, and the characteristic scales are Fcx and Fcy. So, I will not go through all the details of the governing equations because these have already been worked out. So, the analysis of the x momentum equation gives a choice of the pressure scale, which scales with 1 by epsilon square. Then we can rearrange the x momentum equation, and the various terms are shown here, and similarly we can do analogous stuff for the y momentum equation, and then we can use an asymptotic expansion. So, this asymptotic expansion we can do provided that all variables of different orders must be of the order of 1, which is ensured by non-dimensionalization. We cannot guarantee this always to be satisfied, because why we cannot guarantee this always to be satisfied? We are unsure about certain scales, right? We have selected u as the dimensional u by uc, but we do not know what is uc. So, how can we ensure that u by uc is of the order of 1? That is our hope. So, if that hope does not work, then it may so happen that the individual dimensionless parameters are not of the order of unity, and then this method will not work. So, choice of the scale is something which is very important. However, if the suitable characteristic values can be found, then non-dimensionalizing with the characteristic values almost always makes sure that of the order of criteria is satisfied. So, with the asymptotic expansion, right. Whatever we could not write on the board here, you can see on the slide with all the different terms we expanded in terms of epsilon, epsilon square, you get big expression, but by looking into the equation you itself you can understand that which terms will be important. So, you can have the asymptotic expansion along x leading to this equation, and one of the important considerations is that in the process of equating powers of epsilon we have assumed that epsilon square Reynolds number tends to 0 as epsilon tend to 0, and that is true if Reynolds number is small, otherwise you cannot ensure that. Similarly, the y momentum equation and the continuity equation, we have not yet used the continuity equation. So, these equations which we have obtained of the order of epsilon to the power 0 are also known as the leading order equations in asymptotic analysis terminology. So, these are certain terminologies in mathematics, and the reason is self explanatory because these are the leading order representatives of the leading order effects in the physical system. The particular form, this is some note on the asymptotic analysis. The particular form of the asymptotic analysis that we have applied here is called as regular perturbation. There are different types of perturbations which are possible, this is called as regular perturbation. It is regular because a uniform expansion like the ones in the previous equation, equation number 14 is this kind of expansion. This kind of expansion is valid throughout the domain. It cannot be ensured, I will give you some example where it cannot be ensured that this kind of expansion is applicable throughout the domain. So, some further discussions on the asymptotic analysis, this is for those of you who are mathematically minded, but it I mean even if we skip this discussion that will not hamper much of our discussion so far as what we are discussing right now, but just for the sake of your interest, regular perturbation is probably the easiest kind of perturbation. Apart from regular perturbation there exist many other forms of asymptotic analysis, some of which are singular perturbation, domain perturbation, method of multiple scales, the WKBJ theory, method of dominant balance, these are several perturbation methods. I will talk about the singular perturbation a little bit because singular perturbation is something which is also very important in fluid mechanics. So, the reason I will talk about the physics where the singular perturbation is required. So, if you are considering a boundary layer, let us just go to the board to little bit to draw a sketch and understand. Let us say that you have a high Reynolds number flow, so you have a thin boundary layer and the remaining fluid is behaving like a inviscid flow. Now, the viscous effects are important in this region which is very thin as compared to the total dimension of the problem. Question is, can we neglect this region altogether? If we neglect this region altogether, the problem is that we neglect the viscous effects altogether and mathematically we bring down a second order PD to a first order PD, because when viscous effects are not considered the Navier-Stokes becomes the first order PD, second order effect is not there. So, this particular region has to be considered, but the problem is this region is small. So, if this region is considered, the resolution of this region may be lost until and unless you blow up or zoom up this region and apply a different asymptotic expansion in this region. So, applying a particular asymptotic expansion for this region and applying a different asymptotic expansion for the remaining bulk is something which is of the order of the day for a case where a thin boundary layer exists, because you have to resolve the boundary layer. So, that kind of perturbation where you treat this differently is called as a singular perturbation. And the whole idea is that, like, physically try to understand that this is a small region. So, to make it prominent, you try to apply a transformation so that this small region is magnified, as if you have a magnifying glass. By putting a magnifying glass, you have magnified or stretched the boundary layer region and have applied a transformation to achieve that stretching. This is called a stretching transformation. Okay. So, this is something, this singular perturbation theory is commonly used to analyze the boundary layer type of flows. So, singular perturbation is also important. So, let us look into the summary. So, perhaps you have already encountered singular perturbation in your fluid mechanics course. The other widely used name of singular perturbation, boundary layer theory will perhaps sound more familiar to you, but singular perturbation is a general mathematical treatment and boundary layer theory is a special case of application of that. A perturbation series usually involves expansions in terms of small valued parameters, which is epsilon is the present problem. A general perturbation series has the form, you can see that y is equal to summation of f k epsilon into y k x, where f k's are known as gauge functions. Here the gauge functions are epsilon, epsilon square, epsilon cube, like that. So, you can see the lubrication equations summarized. I mean, in the special case that I was working on the board, I neglected the body forces, but if you keep the body forces, this is what the equations will look like. And then the transformation, we attach our reference frame to the bottom wall as shown in the schematic. It moves along the x axis with a particular velocity. Whatever I mentioned as u star in the board, that is given as u tilde in this particular slide. So, this is u star. So, the dimensional boundary conditions at y is equal to 0, u is equal to minus u star. The boundary condition at y equal to h, again u equal to 0. The u boundary condition is good enough to calculate u0, but that is not good enough to solve the pressure distribution, because you have to link it through V. So, you require a boundary condition for V, and that boundary condition is V is nothing but del H del T, right. The rate of change of the height with respect to time is V. So, this is like the kinematics of the problem that is deciding. So, it is just a kinematic parameter. These kinds of boundary conditions are also called as kinematic boundary conditions. So, in the non-dimensional form, the same equations in the non-dimensional form. Now, the choice of scale, very important. If the x motion of the upper plate is dominant, so you have to see that what is the physics. As I told you that the choice of the scale depends on the physics of the problem. So, if the x motion of the upper plate is dominating, then the velocity scale is nothing but the velocity of the top plate. If the y motion of the upper plate is dominating, then the dominant velocity scale along y is your v tilde, and the dominant scale along x is that divided by epsilon, because Vc by Uc is epsilon. If the x body force is dominant,